Hello everyone. Imagine describing the movement of a football sailing through the air. We can often treat it as a single point mass to make life simple. But here's the catch. Real bodies are not just points, they have size, shape, and thousands of particles inside. That's where the idea of an extended body comes in. Think of your school bus. You can't just call it a particle, right? It's a system of many parts moving together. To study such motion, physicists introduced the idea of the center of mass, a kind of balancing point that tells us how the body as a whole moves. And when we deal with extended bodies in motion, we often treat them as rigid bodies, meaning their shape doesn't deform, at least not noticeably. This makes analysis manageable. So let's begin our journey into rigid body motion. Picture a rectangular block sliding smoothly down an inclined plane. What's special here? Every single particle of that block has the same velocity at any instant. This is called pure translational motion. The orientation of the block doesn't change, it glides without twisting or turning. Mathematically, we'd say the velocity of particle 1 equals the velocity of particle 2 equals the velocity of all particles at that instant. It's like when you carry a tray of glasses across the room steadily. Everything moves forward together without rotation. That's the beauty of pure translation. Now compare that with a cylinder rolling down the same incline. This is where the fun begins. Different points on the cylinder have different velocities. For instance, the top of the wheel actually moves faster than the center, while the point of contact with the ground is momentarily at rest, velocity equals 0. Amazing, isn't it? This combined motion is translation plus rotation. It's the physics behind how your bicycle wheel spins forward while also carrying you ahead. Without this combo, rolling would be impossible. Next, think of a ceiling fan. The blades are pivoted around the central hub. Each point on the blade describes a circle around the fixed axis of rotation. For a point at distance r from the axis, the path radius is r, and the velocity vector is always tangential. Particles lying exactly on the axis at r equals 0 remain stationary. So in pure rotation, every particle has the same angular velocity, even though their linear speeds differ. That's why all the fan blades stay perfectly synchronized. But not every rotation is so simple. Take a spinning top. Its axis itself wobbles, sweeping out a cone. This motion is called precession. Similarly, the axis of an oscillating pedestal fan shifts side to side as the blades rotate. These are cases of rotation with moving axes. Fascinating to watch, but harder to analyze. In this chapter, though, we'll mostly focus on the simpler case, rotation about a fixed axis, like the wheel of a potter's wheel or the blades of a ceiling fan. Here's a comparison that clears it all up. Imagine moving the same book across a table into different ways. Case 1, slide it straight, that's pure translation. Every point moves the same, and the book's orientation angle doesn't change. Case 2, push it so it both slides and spins. Now, points on the book move differently, and the orientation angles change over time. In both cases, the center of mass follows the same straight path. But only in the second case does the book's orientation change. That's the subtle difference between translation alone and translation mixed with rotation. Let's test our understanding with a quick classification game. First, a book sliding flat across the table without tilting, that's pure translation. Second, a wheel rolling smoothly without slipping, that's translation plus rotation. And third, a fan blade spinning about its hub, that's pure rotation. The trick is simple. Check whether all points share the same velocity, whether they all revolve around an axis, or whether both effects are combined. With practice, you can identify the type of motion in seconds. So to wrap this up, real bodies aren't just particles, they're systems of particles. We describe them using the center of mass and the concept of a rigid body. Rigid bodies can show three basic kinds of motion: pure translation, pure rotation, or a combination of both. The center of mass always traces the translational path, while orientation change reveals rotational effects. This foundation sets us up for deeper studies into momentum, torque, inertia, and dynamics of rotational motion. I hope this gives you a crystal clear picture of how everyday motions, from a sliding book to a spinning top, fit into physics. See you in the next session, where we'll dive deeper into the center of mass, the heart of all motion analysis.